All right, I'll get started. So welcome everyone. My name is Matt. I'm a lead engineer at Ubisoft Australia. And today I'm going to talk a little bit about the optimization process and kind of some of the complexities that I've encountered trying to optimize some of the games we've worked on and some of the techniques we've used to kind of get around these complexities, answer some questions about our game's performance, and really allow us to move forward with it. So first, a little bit about myself. I've been in the industry for a while. I started my career in Melbourne, working at companies like Transmission Games and EA Visceral. But for the last 10 years, I was in Canada. I worked for Ubisoft Toronto on many of the key projects over there. But now I'm glad to be back in Australia, still with Ubisoft, working on XDefiant. And really, what I'm going to talk about today is my experience around some of the most recent games that you see on the timeline up there. So today, really what I wanted to answer is kind of some basic questions about our game's performance. Things like, what's my frame rate? What should I optimize next? Or how can we be better prepared? And I found that even answering those simple questions is actually quite challenging to answer accurately. So I'm going to go into some techniques that we use to delve into those topics. First, some disclaimers. I'm going to show a lot of charts, some graphs, some performance captures. Those numbers do come from real game builds, but I've kind of massaged the data to make it a bit more interesting. I've obfuscated a whole bunch of stuff that I didn't want to show. So really treat all that stuff as examples and inspiration on the sort of things you can do or charts you can put together to understand your game's performance. So it's real-ish data, but not super accurate. So the first question, what's my frame rate? It sounds super simple, but actually there's a lot of work you've got to do behind it to get to it. So I'm going to talk about how we can define frame rate in the first place, how we can measure it using telemetry, how we can enrich this data with context, and finally, how we can make it more accessible to the rest of our team. So when I used to think about frame rate, this is the kind of picture I had in mind. So this is a benchmark that I've taken from Far Cry 6. It basically runs a little test scenario in your game for about a minute. It measures the frame rate. So you get this nice little graph with a yellow line of the frame rate that it's seen during the benchmark. And then you get a summary at the end that tells you the average FPS. And so, you know, I can tell my friends, hey, my PC is really cool. It runs Far Cry at 59 FPS. But when I'm talking to my friends about that average FPS, in their mind, they're going to picture this graph that I've had a very solid frame rate the whole way through. Everything's great. But average could mean something very different. It could be something like this, where actually my frame rate went up and down. It was all over the place. Sometimes it was really good. Sometimes it was really bad. But the average is still the same. So which is it? And really, for me, what I've realized is that reporting the average FPS for your game or the average frame time, it's not the best measure of your actual player experience of frame rate because it can mean very different things. So what can we do? Kind of alternative statistic to represent that is to look at the median. So this little histogram, that's something I've pulled from, I think, an automated test on Watch Dogs Legion at some point, but it kind of shows a distribution of the frame times that were observed while doing this particular test. And it's kind of bucketed into little slivers of time. And really the median means 50% of our frames were below that threshold. So half the time we were running at this number or faster. But we care about more than half our frame rate. So really, usually we want to think about percentiles, 70th, 90th, 95th. So here you can see the 95th percentile, that red bar down the right. It's kind of 32.8 milliseconds, which means 95% of the time, our player is having a frame time of 32.8 milliseconds, which is really good because the game here was targeting 30 FPS, so we need that number to be below 33. And so here I can say with confidence, reporting that 95th percentile, hey, my player is having a good time most of the time. And a way, so those histograms were quite complex. There's a way I like to summarize it a bit more simply these days, and is to have much bigger buckets for frame times. And again, measure every single frame, but put them into more coarse buckets and color code them with my interpretation of what's a good or bad frame rate. So you can sort of see here, this is from a 60 FPS game. Dark green is like 60 or better, light green 55 to 60. And then we start going yellow, orange, red, and purple when it's really bad. But I can look at this graph and go, okay, the green section, which is what I care about, it's, I don't know, 27, 28% of the time. So long way to go. It's probably still quite a bad player experience, but it gives me a much better way to picture sort of where we are with the frame rate or the frame times in our game. And so now that we understand the kind of statistics behind frame time, we can set some KPIs, some key performance indicators for the target frame rate that we might want for our game. So an example here is we might want to say that 90% of the time we want to experience 55 FPS or above. And so that's a single number we can report that gives us a much better picture of our game's performance. And if you flip that the other way around, really what it means is that our 90th percentile is 18.2 milliseconds or better. Now we might want to have complementary KPIs. So if 90% of the time I'm good, we don't want the other 10% to be my game is completely frozen. That's pretty bad. So we might want to have a second KPI for the spikes and the worst cases, and saying basically none of the time, less than 0.1%, whatever. We don't want to drop below 30 in this example. But again, we can tailor that to what we want for our specific game. So now that we know the kind of KPI that we want to set for our game, we want to measure it. And there's lots of ways to do that. And typically, initially, it might just be you as the person responsible for performance, kind of playing the game, collecting frame times. I mean, you could probably write this out to a CSV and calculate it using Excel, but very quickly, you're going to run out of hands. Like a single person can't test every scenario in the game. So very quickly, you might want to bring in your QC team to help test more cases. Or maybe your game is multiplayer and you literally need people to play with, and one person can't do that. And ideally, you probably have an army of robots. You want to have automated tests that can cover all of the scenarios, every single kind of corner cases that humans can't cover. Maybe you want to have some automated tests that, again, are going to do the same thing and generate performance data that you can collect and measure. And yes, then you might also have lots of platforms that you need to test independently, because different platforms might have different KPIs or different performance numbers. So you need to cover that too. And really, this turns into a lot of data that you have to collect and aggregate together and kind of be able to visualize. So one of the techniques that I like to use for this now is actually similar to player telemetry. Quite often, our games these days already have telemetry systems that collect a lot of data from game clients. So thinking like damage done to enemies, damage received, health, kills, and we use that to balance our games. But that infrastructure can also be used for other stuff that's not player-facing, like performance data. And so I like to use similar approaches to do the same kind of thing, where we can have game clients sending performance telemetry live to a database, and then we can build dashboards and reports on top of it to understand what's going on. So this is a tool. There's a tool called Grafana, which is a pretty open piece of software that I've been using a lot recently that helps me visualize this kind of stuff. And really, it's a web-based interface. You can connect it to your telemetry database, and it's super easy to create dashboards and reports. You can click a few buttons, and you can get a pretty cool-looking dashboard that can summarize your game's performance. So Here I've chucked in an example, some few interesting stats that I've pulled from a game build. So things like the GPU times, because we care about those as much as we do about CPU times. A few systems that are interesting, that might be spiking, that I want to keep an eye on. And maybe on the right-hand side, just a timeline of the frame time that we're experiencing over time. One thing to note too is that there are capacity limits to how much telemetry you can send, even with these kinds of systems. So here we're actually aggregating some of the frame times on the client and kind of sending a 1 second average to the database and then showing that. But it's worth to keep in mind because aggregation is always going to lose some information. So you've got to be aware of whether the data you're looking at is aggregated or it's capturing every single frame. So now we have a lot of game clients, automated tests, QC, generating performance data, performance telemetry, but we need to make sense of it. So when you look at a dashboard, you need to understand where the data came from. Am I looking at data from an automated test, from a QC test? What platform was it on? What build number were we running? For example, if an optimization came in the latest build, am I seeing the numbers before or after this optimization? What was the player doing? If you're in the menu versus in the game shooting lots of enemies, the performance numbers that you see are going to be very different. So you need to understand what the player might have been doing at the time at which the data was collected. And so really it means we need to add context to our performance data. So one of the databases that we're using for telemetry, it's called Influx. It's, again, an open piece of software. It's what we call a time series database. So it's designed to collect a lot of data where the main axis is time, which is perfect in this case because we're kind of measuring performance at every frame, and there's a time associated with that. And the advantage of this kind of database is that we can add arbitrary tags to each data point that we collect. And it's basically name value pairs. So here we've added tags to the data, things like the platform we were running on, or the build number, or the username in this case, and even gameplay context. Am I in the game? Am I in the menu? What screen am I on? That kind of stuff. And with this context, we can then filter our dashboard. So in Grafana, we can configure filters to restrict the data that we're looking at. So if I want to look at performance numbers from a particular test, on a particular build, on a particular platform, I can zoom down on this and really get a better picture of what's going on. Or you can do side-by-side comparisons. Have a dashboard that compares numbers for your different platforms so you can see them next to each other and get a better understanding of what the differences are. And really, the key benefit of doing it that way is accessibility. Grafana is a web-based tool. Anybody can go to that web page, click on a few buttons, and get to their performance data. You don't need any tools or a programmer helping you. Anybody on the team can be playing the build, going to a website, and basically seeing this data live because this telemetry is collected real time, which is super cool. And then we can, with this kind of dashboarding system, we can boil it down to generate those performance KPIs that I was talking about earlier. We can get our dashboards to aggregate the data and generate that number that tells me what percentage of the time am I experiencing a good frame rate. And then it's super easy. I can generate the dashboard. I can show it to the project's production and say, okay, this is the state we're in right now. You might see from this example, those numbers are quite low. This is not a good player experience, but it kind of shows an example. Completely different example. So this is from Watch Dogs Legion. It's we had this automated test that basically had an AI driving around automatically on a pre-crafted circuit around the city of London. And at every regular intervals, we would report the player position and the frame rate they were observing through the telemetry systems. And then we had some scripts that kind of sucked this data from telemetry and generated these really cool heat maps. So then we could look at the heat map. You can see there's a little red square there that tells me, okay, this area of London is more expensive for some reason. Maybe I want the content team to kind of check out this area and see what's going on, what could be more expensive. And so, so that sums it up for talking about frame rate. Really, the first step when you want to optimize your game is to understand what your frame rate is. How are you going to measure it? What are your KPIs? Statistically, how you're going to calculate your game's performance. Think about things like how you're going to collect this data using things like telemetry. Make sure you have enough context so you understand where your data is coming from. And finally, make sure this data is accessible so anyone on the team can really get to it easily. So the next question, what to optimize next? Optimizing games is really hard. It's very time consuming. Your game might have thousands, millions of lines of code, tens of thousands of assets. You can't make the entire thing run optimally. Like it's impossible to go through all of your code and all of your data and make it perfect. So you need to prioritize and pick the worst areas and get the most bang for your buck. So I'm going to talk about the traditional approach, the way I've always done performance analysis to kind of find the hotspots. Again, talk about adding context to this information. Then we're going to take a fun little road trip to talking about data science. And again, we're going to talk about making this data accessible. So let's start with a traditional approach. The way I've always done performance analysis is using analysis tools. So things like here, Intel's vTune will take a snapshot of a frame of your game, and you kind of get a timeline of all the different functions that are executing in this given frame, how much time they're spending, and you can sort of get a picture of what's going on in your game's frame. And there's a lot of tools that do this. So Intel makes vTune available. RenderDoc is a similar tool for GPU analysis. Sony and Microsoft provide their own tools as well, so Pix and Razer. And at Ubisoft, we have our own tools. So the Snowdrop engine, which is one of the big engines that we use for many of our games, it's got a profiling tool as well with a very similar kind of visualization. So you can see this kind of timelines for all the different threads. We show the different functions executing on those threads, and kind of you can get a picture of what's happening. And of course, what you do then is look at this picture and look for the expensive bits, the big blocks, the functions that are spending too much time executing. That kind of tells you what you should optimize next. Now, it's important to have context in those captures as well. So showing the function names in the profiler tools comes from contextual information that we're passing to it. And usually you'll get APIs that can place an arbitrary string on the stack. Maybe it's a function name, maybe it's something else. So here I've showed that you can profile the function, but you can also put in an arbitrary string that tells you, hey, this is a potentially expensive section of my code. I want to be able to identify it specifically in my profiler tool. Other interesting ways to add context. One is assets. So in this example, we've got a classical render loop where you're iterating through hundreds of objects, rendering them all. And let's say one of those objects is more expensive to render. If you just look at it with function names, you're just going to see that this one call to the render function is expensive. Why is that? I don't know. But if you tag it up with the name of the asset, you can get a better sense of, okay, it's this particular thing that's more expensive. Maybe it's got too many polys. Maybe I should get the art team to take a look at it. And you'll see how useful this is later on. The other one that is useful is marking up systems. So again, pretty classic example, a manager that has an update loop and a render loop, and we mark up both of them with the same name. So here, and then the performance numbers are tallied up later on in our profiler tools, and I can get an overall picture of how long am I spending dealing with UI overall, even though there's multiple systems in different areas that are actually processing UI. So an example of how we use this context in the Snowdrop profiler. First of all, color coding. Each system gets its own color associated with it. So I can look at a performance capture. I don't even have to show function names or anything. I can just look at the colors and kind of get a sense of what's happening in my frame just by seeing the size of the green chunks or the size of the orange chunks. And then when we zoom in, you can still find out the function name. You can see the system that was running at the time. But if that function was processing an asset, we show the asset name in the tool, which gives us more information as to what was going on. So this is kind of the classic way of doing performance analysis. This is the way I've done it many, many times. You take your captures, you look at your captures, kind of one frame at a time, right? And this is the question that's always hard to answer is the frame I'm looking at representative of what's going on in my game? And normally, you'll capture lots and lots of frames, you'll manually scroll through them. Maybe your tools let you take a bit of a step back and see what's going on across dozens, hundreds of frames, but it's always very hard to know exactly, am I doing the right thing, right? Is this particular frame the one I should be optimizing, or should I be optimizing others? Questions like which systems are the biggest contributors? Again, you can get a sense of that by looking at frame captures kind of a few at a time, but it doesn't tell you necessarily the overall picture for your game. Setting budgets, super hard. What's the right amount of milliseconds any particular system is allowed to spend? The other tricky example is determining the overhead for a particular feature. So if you think about an example where the player throws a grenade, the grenade explodes, it damages the environment, this is a sequence that takes hundreds of frames. And so if you're looking at captures one frame at a time, it's very hard to know exactly what's going on with this feature, because depending on the frame you're looking at, there's very different things going on in that sequence. So what can we do? How can we get to this higher level picture? So the first thing we can do is leverage the fact that we can take a lot of performance captures. We can have our QC team taking captures for us, our automated tests taking captures for us, and generating this hundreds of frames of very detailed performance data, and start analyzing it at a higher level. And unfortunately, many of the performance tools that we have aren't very good at doing that. So we started looking for other ways to do this. And really, the breakthrough here is to think about performance data as data. If you look at a performance capture and you dump it in a table, really it's nothing more than a whole lot of rows with the function name, the time spent executing that function, the system that might have been active at the time, the asset that this function was running on, and an ID for the current frame. And so really those performance captures that look like a sexy timeline in a profiler tool, if you boil it down, it's data. And it's data with lots of it. Once you have a single frame, might have thousands of rows for all the functions. When you want to look at thousands of frames, you end up with millions and millions of rows of data. And so when we start thinking about analyzing this, we really start entering the realm of data science. And now, unfortunately, or fortunately, depending on how you want to look at it, the best ecosystem for data science is all based in Python. So There's libraries like pandas, which are designed to process millions and millions of data points really efficiently and analyze those data points, generate cool summaries, and do the heavy lifting of analytics. And then things like Seaborn and Matplotlib are visualization libraries on top of that can render efficiently, again, charts that summarize all these millions of data points. And so this is what we started doing in some of our engines at Ubisoft. We take the kind of binarized performance capture files, we process them in Python, we convert them to this Parquet format, which is it's kind of an open format for tabular data, and we process it in Python using pandas. And we've actually taken this one step further now, is that we actually process this data and stick it in a database, in a proper database, so that it can be accessible by many different endpoints. So we can still get to it in Python, but we've started building web interfaces to access this data and make it easier to get to. So now I'm going to start showing some of the examples in some of the ways we start using this data. So this is kind of one of my go-to visualizations when I first want to get a sense of what's going on. Really, what we're doing here is breaking down the time spent executing individual systems across the thousands and thousands of frames that we've collected, so we can start getting a sense of the cost of individual systems. Now, the important piece here is the box plot. That's kind of what everything relies on. So it's called box and plots in Seaborn, or letter value plots. And really, what it means is that each box holds an amount of the data that you're looking at. So the biggest box holds 50% of the data. And so the extremities are kind of the minimum and maximum for all of the data points representing the time spent across multiple frames executing that system. And then you can go down a step and you're adding half as much data every time. So the next box down adds 25%. So those two boxes combined sort of shows the breadth of 75% of our times measured, and kind of so on and so forth. You add half as much every time. And finally, what's also super important is that you see the outliers. On the very end, you have the once-off spikes that are marked on the box plots. And this is useful because that tells you whether a particular time really is a once-off, or it's actually, your system is actually that expensive. If it's an outlier, you'll see it sitting on the end. If the number is inside a box, that's actually something you need to think about. It's a typical cost. So if we go back to that original box plot, we can start seeing some interesting things. So first of all, the object system, you can see it's the most to the right-hand side of the graph. So it's the most expensive. The bulk of the data, here in this case, it was kind of 10 to 20 milliseconds. The biggest box is quite wide, which tells us that it's very variable. It's a system that on a typical frame can cost anywhere between 10 or 20 milliseconds. So the variability is a concern, and also the fact that it's the most expensive system in this picture tells me that I should be spending some time looking into this. And here the object system was kind of game logic for props in the game, so like things in the environment, maybe think like Unreal blueprints executing logic on game objects. Now, if we look at something else, the audio system here, the box is very narrow, it doesn't change very much, it's a fairly constant cost. So at least this tells me that the overhead of my audio system isn't going to change terribly much. So that's good to know as well. So maybe I don't have to spend as much time worrying about audio right now in this case. Now, this object system was a bit worried, so we wanted to spend some time investigating what was going on there. And so one thing we can do is, it's a different type of box plot. Instead of breaking it down by system, we can break it down by asset. So we can do the same kind of chart, but show the time spent executing various assets. And more specifically, we are only showing the assets that are part of the object system. So animations aren't going to show here, or audio assets aren't going to show here, because I'm filtering just for the objects. And when we did that, there's a pattern that became really obvious, is that a lot of the assets were weapons. And actually, that was kind of unexpected for us. It felt like there was way more weapons being executed than we were expecting. And when we drilled down into it, what we found was that when you killed an enemy, they would drop their weapon, it would stay on the ground, maybe you could pick it up later or whatever. But the logic for that weapon on the ground was continuing to execute, even though it didn't need to. It was just a weapon sitting there doing nothing. And so what would happen is you killed more and more enemies, they would drop their weapons, they would all be on the ground, and they would keep accumulating and causing more and more problems. And I don't know for sure, that explains the kind of breadth of numbers we saw for the object system, where as you played the game more and more, this system became more and more expensive because more and more weapons got dropped. And probably there was a cap on spawning limits, so it never exceeded a certain value. But doing this kind of analysis really helped us kind of see the pattern and solve it fairly quickly. Now, completely different example, budgets. Setting budgets for performance budgets for games is really hard. Like I find that quite often I'm just kind of sticking my finger in the air and picking a number that sort of says, yeah, based on my experience, this is about so many milliseconds you should be spending on this system. And that's a valid way of doing it, but we can use data to do this a bit more accurately. So one of the tricks that we do here is we take the same data, but we split it into two groups. One group is the performance numbers for good frames, as in frames that run at the target budget that we wanted, and bad frames, which is obviously frames that exceed that budget. And nicely colored red and green, and you can render them side by side in your box plot. And so let's take an example here. If we zoom in on animation, you can see when our frame rate is bad, our animation system is much more costly. And so maybe our budget for the animation system should be somewhere around the median when the frame rate is good. That might be a good way of doing that. Of course, I could be completely wrong. Like, it could be that animation system spikes up because there's lots happening on the screen, more characters animating, and we need to find the time from somewhere else. And maybe our budget for animation system should be the red budget. I don't know. It doesn't give us all the answers, but it gives us more information to be able to do this better. Now, the next one that I talked about already is getting a sense of the overhead for a particular feature. Here, what we've been doing is doing this with two captures and comparing two captures side by side. So one is a capture of the player being idle, so kind of sitting there doing nothing, and one is a capture of the entire sequence of the feature being activated. So player throwing a grenade exploding, having a capture with that whole sequence. And then we can, again, compare the two side by side and start getting a sense of the overhead of that feature. And if you zoom in a little bit, you can see the orange here is the in-action capture, and you can see, the render system is being stressed a bit more, the kind of game logic is being stressed a bit more, so that gives us some hints as to what the overhead of that feature is in our game. Another way that I like to get a better sense is to kind of do a diff between the two captures and break down the assets that only show up in the in-action capture. And so for the grenade example, you might have the grenade object itself, the VFX that trigger when the grenade explodes. And so when you start filtering on just those assets, it's likely that if they're only in action capture, they're assets relevant to that feature that you're measuring. And again, you can get a better sense of what the overhead of that feature is. And finally, we can collapse it down to a single box plot where we just, for every frame in action capture, we tally up the time spent executing all those specific assets and summarize it as a single number. And then we can see the distribution of time spent executing all those assets across all our frames. And so that gives us a kind of sense of what the overhead of that feature is. You can see there this particular feature, the range of time spent, between 0.2 to 1.0 milliseconds, because it's a feature that has a lot of steps and goes up and down. And you can see the worst case as well with the outliers down the end, the kind of 1.4 milliseconds. And so we can use that to better understand a feature's overhead and maybe even start setting a budget for the amount of time that is acceptable to spend executing a particular feature or a player action or whatever. And so this was kind of one of the big breakthroughs for us is once we started collecting a lot of performance data in large volumes, doing the statistical analysis on it, it's really started to help us identify higher level patterns in our game's performance and really focus our efforts a little bit better in terms of where we need to be spending our time optimizing. Now, this isn't the solution to everything. There's still a lot of value in using your profiling tools, looking at individual frames one at a time, but this is another way to help focus your efforts. And the key again here is accessibility. So I mentioned earlier that we're now able to store our performance data in the database and have a web interface on top of it. So here's a kind of screenshot for the kind of web version of what I was showing before, because what I was showing before was basically Python scripts that we run to generate those charts. Here it's a website, so anybody can go to that website, get to their performance data. So here I've shown an example where I'm showing the animation assets and the similar kind of box plots of the time spent executing animation assets. So an animator could go and get to this data with no help from any programmers whatsoever, that you can just go find it from all the data that we're collecting. And we even have cool features like if you see a spike, it's connected to the original performance captures. So on the website, you can click on the spike. It's going to download the original performance captures from the network, and you can pop it open in your original profiler tools and see what was going on. So it's getting quite powerful. The other advantage of doing this kind of analysis in Python is I'm pretty lazy. I like information to be fed to me. So Python is very, very easy to script. There's a lot of powerful tools you can use. So now we've started to have scripts that suck down performance captures, do the analysis, generates reports, email them automatically, so we can just have this data pushed to us very easily. And so takeaways from this, again, make sure you have contextual information in your data. Look at data science kind of techniques to analyze this data at a higher level. And again, no matter what, make it accessible. Make sure as many people as possible on your team can get to this data. So finally, just touching base a little bit on how to better, I'm going to give one example on how to better prepare for the performance optimization pass on your games with a real life example. And then I'm going to talk about a technique that I'm a big fan of that we're calling performance scaling. So this is a real lesson from Watch Dogs Legion. One of the platforms that we were targeting, we were doing a lot of our performance testing using emulation, so kind of hardware emulating the target hardware that we were aiming for. And we thought we were doing pretty well, but what we discovered very late in development was that running our game under emulation was about 10 or 15% faster than running the game on the real hardware. So we kind of had the, oh shit moment, we need to find another 10 or 15% frame rate very, very late. Now, obviously, the real lesson here is be aware of your target hardware's capabilities, test on the real hardware as much as possible. But that's not what I'm going to talk about. I'm going to talk about a technique that helped us a lot on Legion get to our frame rate targets and really help us get that 10 or 15% relatively easily very late in development. So this technique is kind of analogous to what a lot of games do on the GPU. On the GPU, many games use dynamic resolution. So when the GPU is under stress, we reduce the resolution of the back buffer, which means less pixel shaders are being executed, makes it easier, less strain on the GPU, and we can kind of hit the target frame rate again. And really the theory with performance scaling is that we want to do the same on the CPU. It's a little bit harder, but it's the same idea. And so again, we track a value that we call the performance scaler based on the CPU load on the game. So simple number between 0 and 1. When everything's perfect, the number is 1. When your CPU load is over budget, we kind of ramp down towards 0 and back up again when things are going fine again. And the real trick and the challenge is to have as many game systems as possible read that number and scale themselves. And really, when the number is 0, that's an indication to all of your game systems that really you should be ramping down whatever you're doing that's costing CPU. Yes, it's going to lower the game's quality, the same as dynamic resolution, but it's going to hit the frame rate that you want. And we use this technique quite a lot in Watch Dogs Legion. So in the end, we ended up having 2 global scalars in Legion, one for the main thread and one for the worker threads. And then we had an emergency mode when things got really, really bad that kind of turned off everything, basically. But we used those scalars for many different things, actually. So one thing that was quite expensive was spawning entities was pretty taxing on the CPU. So we modulated our spawning frequency by the performance scalar values. And we also modulated our spawning budgets, so we would end up having less entities in the world when the CPU was under stress. Our AI systems used that quite a lot as well. So our AI was already time sliced. It already had time budgets that kind of allocated so many milliseconds to run per frame. But we used the performance scalars to reduce those budgets even more to get to the frame rate that we wanted. And when the CPU wasn't under stress, we could spend more time executing AIs in a given frame, which gave a better result. And we also use this for kind of rendering systems that had a CPU impact. So things like shadows, we would reduce the shadow distance, running partial updates on animations for characters that were further away. All of that kind of helped, and that really helped us get to the frame rate numbers that we wanted for Legion. On all our platforms, we actually ended up tuning some of those numbers kind of per platform to make sure we maximize the quality on each platform, but still hit the frame rate we wanted. So really the takeaway from here is have a contingency for your worst case. Like I said, optimizing games is really hard. And so it's likely there will be things when you get close to launch that won't run at the frame rate you want. And so you want to plan for these worst cases and have kind of things you can do at the last minute to get the frame rate that you want without spending all night kind of optimizing something. And I talked about performance scaling as a good example and a very successful techniques for us on the CPU side. But really the kind of overall idea here is be prepared. Be prepared for what's going to come when you need to optimize your game. And actually, this is kind of my conclusion for this whole talk. I wanted to provide some things to think about on how you can be ready for the optimization phase of your game. So think about your KPIs for performance. How are you going to measure them? How are you going to collect them? What techniques are you using to collect performance data? Telemetry, performance captures. How are you going to analyze this data? Looking at data science and dashboards and better tools to really understand what's happening with your game's performance. Making sure this data is accessible, so it's not just the one engineer who's responsible for performance that has to answer all the questions, but anybody on the team can get to this information without your help. And finally, planning for contingencies, making sure that you have a plan for when things might go wrong, that you can deal with it at the last minute. And finally, I just wanted to chuck a couple of future ideas on things I want to experiment with in the future. One is adding more context to better understand the kind of matrix of different features that are active at any point in the game and contribute to performance issues. The next one is kind of automatically tuning performance scalars. Performance scalars mean having a lot of game systems be adjusted and reducing budgets and all of that, which has an impact on quality. And so I'd love to be able to tune that automatically to find the kind of best balance of keeping the frame rate high while not reducing quality more than we need to. And I think that's an ML problem. There's probably a neural network we can create that kind of takes all of these numbers and inputs and outputs and tunes itself. And the last one, a little bit out there, but we're collecting a lot of performance data for all of our functions. And it'd be pretty cool if, as a programmer, I'm kind of working on a function and it kind of looks up the performance in the field of that particular function. So if it's expensive, it might tell me, hey, Matt, be careful. You're touching something that's already really expensive. Maybe don't make it any more expensive, please. And really, that's it for me. Few minutes for questions, but you can hit me up afterwards. And yeah, that's it. Very short.
Great talk.
Thanks.
I'm going to steal some of that stuff. It's great.
It's okay, I'm going to steal your stuff too, by the way.
Cool. So some questions. You're saying you get your performance scans and they get chucked into a database and analysed. Are these like human-triggered performance scans, or are they automatically done?
It's automatic, actually. Our game builds now can automatically dump the data and upload it to somewhere in the cloud, and then they're sucked out of the cloud and processed automatically. Okay.
What time spans we're looking at here? Like for the length of the profile?
So it's a few seconds. It's a good point, though, that collecting all that performance data has an impact on the game. It takes up a lot of disk space. And so, yes, we don't collect everything. It's kind of a sample, like every 15, 30 seconds. We'll take a couple of seconds and upload this. And by doing that a lot, we're hoping that it gives us a good enough picture of what's going on. Yeah. So yes, there are gaps.
Awesome. Yeah, the box and plots are a fantastic idea. Thank you.
Yes.
I think it's probably. I think you probably answered it in the way that you sort of presented the stuff here. But when you do the performance scalars, everybody treating that as a flat number to run their systems on, or are the systems deciding to divvy that scalar up based on what priority the system should have?
No, yeah, it's an overall number. So it's a number that represents the overall state of the game, really. And so it's really telling your game system that hey, performance is bad, we need you to help. So it's not divvied up, no. We've kind of experimented with breaking it down per system, and we may still do that. Like it's still, we're still trying different things as we work on different games. And it's also, every system, it's up to them to interpret the numbers how they want and scale themselves. So it's very much, the expert in that system is kind of expected to deal with it and do the right thing as best they can.
We want one more.
Do you worry about the performance scaling, like cutting out most of a system because, say, animation ramps down really hard and you just end up with no characters animating so that the budget can be spent on all the other systems?
Yeah, no, and that's fair. And so again, let's say the animation system is interpreting the performance scalar, it's still got to have a minimum value below which it can't go. So even if you implement performance scalars and every system kind of cranks down as far as they can, you might still be over in your frame rate. You might still have a problem, and then you've got to find other ways. Like it helps, but it doesn't solve everything. And yes, you have to be careful not to wreck your entire game. Like it's got to be a sane interpretation of the performance scalar. Like it still has to make the game playable.
It's a cool idea, so I'll try and steal that myself too.
All right, thank you very much, and lunch is served.